Hello, this is paper CSCI 3326, and I'm Peter Maurer from the Department of Computer Science at Baylor University in Waco, Texas. And my email address, as you can see on the screen there, is peter_maurer@baylor.edu. I'm here to talk to you about computer science theory from a practical point of view. Although a rigorous and thorough course in computer science theory is necessary for students who are going on to graduate school, many students do not choose this route. And that doesn't mean that theory isn't useful for these students, because every student can benefit from some grounding in computer science theory. But students typically do not like theory courses because they do not perceive them as practical. They ask, what's in this for me? And in terms of going out and getting a job and working a regular job, it doesn't end up being very useful. The primary purpose of this course is to show students how to use mathematical machines to solve practical problems. In other words, their perception of theory is not 100% accurate, but the manner of presentation presents it in a way that's not particularly useful to them. Our course is entitled Foundations of Computer Science and is based on an earlier course of the same name. This course was intended to teach students how to perform program proofs. At one time, this ability to prove programs correct was believed to be a practical tool for working programmers, or at least it would be in the near future. But as time went by, program proofs became less important as a practical tool, and so we decided to upgrade the earlier course with a new course to give students practical tools that are based on theoretical concepts. The new course covers three fundamental mathematical machines: finite automata, push-down automata, and Turing machines. The material on finite automata and push-down automata are the most detailed part of the course. We cover Turing machines only lightly and in a somewhat more abstract way. We begin by teaching finite automata because that's the reasonable place to start. We cover the following topics in this order. We start with deterministic finite automata, regular grammars, non-deterministic finite automata, regular expressions, and then the pumping lemma for finite automata. Now, our rationale when designing the finite is this: when designing deterministic finite automata, the students are introduced to three basic concepts: string recognition, finite counting, and intersections and unions. In string recognition, we cover how to identify a substring in the following positions: at the beginning of a string, at the end of a string, anywhere in the target string, or as a complete match for the target string. Each of these are very similar but slightly different. Now, continuing with our rationale, starting with deterministic finite automata is simply the obvious place to start. And although regular grammars are not especially useful, they provide a strong motivation for non-determinism. That's why we cover them second. We show derivations using finite automata and the transformations used to convert back and forth between finite automata and regular grammars. We note that converting from a regular grammar to a finite state machine often results in a non-deterministic finite automata. We end the entire discussion of these with regular expressions because of all the forms used to define regular languages. Regular expressions should prove to be the most useful for students. Now, string recognition is based on the following type of state machine segment, which recognizes the string 0011 from an alphabet containing only 0 and 1. We call the pictured transitions success arcs because this sequence of transitions recognizes the string. The various positions of the string are handled of the searched for string in the target string are handled by adding failure arcs as well as start and final states to this basic structure. This is merely an example, of course. The problems of identifying a substring at the beginning of a string also allows us to introduce the concept of an error state as in the following example, where if we find since we're looking at something that has to be at the beginning of the string, we find an incorrect character, we know immediately that the string is wrong. And so we have an error state that will absorb all remaining input but not allow a transition into a final state. To show the concepts of counting, we first introduce the following machine, which accepts strings with an odd number of ones. We use this example as a basic motivator for state machines. And we introduce the following type of machine as well that accepts all strings with at least 3 ones. These are two different counting problems, and we also show how to combine these various problems into larger state machines. For unions and intersections of regular languages, we show how to construct a cross-product machine. We don't denigrate the ad hoc method because that works as well, usually. But we start off by showing a naive construction where we generate all of the cross-product states and then show that many of them are unreachable from the start state. We then show a more realistic method starting from the start state to avoid generating these unreachable states. We show how the placement of the final states can give either the union or the intersection of two regular languages. There are also ad hoc methods that could be used, but this is a very straightforward mechanical approach that will work for anything. We wind up our presentation of deterministic finite automata by showing a simple implementation. We present a template for a subroutine that executes one transition per call, returning true or false, depending on whether the new state is final, with true being final. The subroutine accepts one character per call and uses the character \0 or the 0 character to reset the machine if I want to use the machine multiple times. We point out that in practice, more ad hoc methods can be used and are sometimes preferable to the very structured examples that we give. Now finally, we show how to minimize a state machine and point out that the minimal form is unique. We use the standard algorithm for doing that. For regular grammars and non-deterministic finite automata, we begin by showing how to construct regular grammars, giving a precise definition for them. And then we show how to use them for the string matching and counting problems that we covered with deterministic finite automata. We then show how to convert a deterministic finite automaton to a non-deterministic one. Actually, that's reversed. We go from non-deterministic to deterministic. We give an example of a state explosion and point out that the algorithm is indeed worst case exponential because we can end up with an exponential number of states. We also point out by several examples showing that non-deterministic machines are much simpler to use for identifying strings than deterministic finite automata. Typically one has the basic machine that was pictured earlier without any failure arcs because they're not necessary in a non-deterministic machine. Since we have the conversion from a non-deterministic machine to a deterministic one, we can always start with a non-deterministic machine and end up with a deterministic machine which we can actually implement. Now, for regular expressions, we begin by presenting the formal inductive definition of a regular expression, and we also give the state machine equivalence of the basis and inductive elements, demonstrating that state machines can be implemented as regular expressions. We show the reverse transformation, but only as an example because it is complicated. We rapidly move on to the POSIX standard for regular expressions because that is infinitely easier to use than the inductive definition. To give this to the students as a tool, we take the regex package, which is available in both C++ and C, two different versions, and show how to incorporate it into their own programs and the steps that one has to do that. C++ is the preferred way to do it, but it tends to be somewhat buggy. We've uncovered a number of bugs in that particular implementation. Finally, we present the Lex tool and give a runtime example of how to incorporate Lex-generated subroutines in an ordinary program. This is done live. I actually take a description of a Lex specification, compile it, incorporate it into a machine, and the students are generally quite impressed by this because of the simplicity of identifying certain categories of strings or specific strings and the ease with which one can do that. We also show the pumping lemma at this point. It's one of the few actual proofs that we cover in this course, and the main reason that this was left in is because it's very straightforward, although abstract, and we cover it in detail, going through individual steps piece by piece. And then, once we've gone through that, we use the classic example of A to the n, B to the n, to show how to apply the pumping lemma, showing that this set of strings is not regular. This is largely for your information type material. It doesn't take that long to present. And we don't test the students on the pumping lemma itself because this doesn't fit with the spirit of the course. But we do insist that they remember that A to the n, B to the n is not regular. So if I ask for an example of a non-regular language, they have one memorized that they can just pump out. Now, for push-down automata, we actually mainly focus on context-free grammars. The reason for that is that even in applications that use push-down automata, it's generally in a way that is different from the way that they're presented formally. I do give them a formal definition of this, of push-down automata and how they work, but I don't ask them to learn that. It's merely for their edification. Then we go through an example showing how to parse strings of the form A, B, B, B with the above grammar using a stack. And we do this non-deterministically because if one does top-down parsing, non-deterministically you can parse anything using a stack. Our main focus is to present context-free grammars as a method of describing and recognizing or parsing complex text. We don't concentrate on programming languages because this requires material on code generation, optimization, and possibly other topics which are beyond the scope of this course. We do, however, discuss expression grammars because it's an interesting problem, and how we have to go about constructing an expression grammar, especially for top-down parsing, is a very interesting process. For the most part, we concentrate on parenthetical type languages, such as the first one here, A, N, B, M, C, E, I, F, I, D, M, B, N, which is a set of nested parentheses, and then consecutive sets of parentheses, as in the second example. We show how to construct the first and follow sets of non-terminals and strings. We show how to convert these sets into look-ahead sets for productions. We give criteria to show that look-ahead sets are key to constructing a deterministic top-down parser for a grammar. If there are intersections between certain look-ahead sets, then the grammar cannot be parsed deterministically, and we need to either use a different parsing technique or uh, reconstruct the grammar. Now, with expression grammars, we start with the simple and obvious ambiguous grammar. We're concentrating only on the addition operation here. Um, E goes to E plus E, and E goes to V, which is generic for any variable. We use parse trees to show the meaning of ambiguity, but we don't test students on parse trees. It's merely to justify the term and why we come up with this term for this problem. Then we show how to factor this grammar using the standard way of doing it into the following. I introduce a couple of false steps in there so that students will concentrate on what's happening and realize that this is not necessarily a trivial task. Now, with this factored grammar at the bottom here, we are able to obtain acceptable look-ahead sets for the two productions with X on the left, which is the only thing that really concerns us. We also discuss implementing parsers for grammar, starting with a user-created parser stack. This is not as desirable as recursive descent, which we move to reasonably quickly, and presented as the preferred method for top-down parsing. We show how to take a grammar with its look-ahead sets and construct a top-down or a recursive descent parser from that. We also show how to add action symbols to the grammar in case we want to generate code or do other useful things once we've recognized a particular string or particular structure within the input. In other stuff, we show how to recognize non-expression data as something like the following: colors, red, blue, green. We emphasize describing lists with both with and without delimiters, and how to permit or deny empty lists. At this point, we introduce lexical analyzers to reduce the complexity of context-free grammars, and of course that references back to the Lex material that was presented earlier. Now, bottom-up parsing, we begin by pointing out that recursive descent is a method for quick implementation of small parsers, but there's a better way for larger grammars. We show how a possibly non-deterministic parser would parse the same strings that we handled in the top-down material. We introduce the concept and we introduce the concepts of items and states and constructing state tables from them. It's always possible to construct a state table, but the state table may not be deterministic. Now, in creating states, we start with an example that's LR0 and show how to create the LR0 states for this top grammar. A goes to ASB and S goes to X, X being a delimiter between the A's and B's. And then we present an SLR1 example, which we use reasonably extensively because it's very, very simple. It is, however, not LR0, it is SLR1. And we discuss how you know when you have problems, shift reduce and reduce conflicts, and show how to recognize them very easily once you've constructed the set of states. And then we show how SLR1 eliminates some of those. Not all, of course, but some. We then proceed to LR1, which is significantly more complicated, and we tend to concentrate more on the simpler examples than the LR1 examples because even simple grammars end up with a huge number of states, or can end up with a huge number of states. But we show how this eliminates more conflicts than SLR1. Finally, we present the LA-LR1 method of reducing LR1 states. And we also point out that this is a hierarchy of grammars, that there are grammars that are not LR0 but are SLR1. There are grammars that are LR1 but not SLR1. And there are grammars that are LR1 but not LA-LR1. Coming up with a series of examples that shows this was extremely difficult. Now, we also take our states and show how to create tables from them. We use the same set of states to create both LR0 and SLR1 tables, and we show how to use look-ahead sets for the SLR1 tables, or follow sets primarily. We show how to create tables from LR1 and LAR1 states, and show how the differences between LR0 and LR1 and LALR1. Once the tables are created, we show how the parsing algorithm works. We point out that the parsing algorithm is identical for all state tables. We give enhanced examples to show how each state can be associated with a specific terminal or non-terminal. We actually modify the symbols that we push on the stack, which are normally integers, and add some additional information to them to indicate which terminal each state represents, because each one of the states represents either a terminal or a non-terminal that's being pushed on the stack. Now, we wind up by presenting the YAC tool and show how some of the YAC features can simplify the grammars used for actual projects. You can use ambiguous grammars to represent expressions and have some additional notations that you can add to resolve the ambiguity. And we'd like to end up by assigning a parsing project for simple notation like chess moves, bridge games, or a myriad of other things. Only one per semester, of course. But unfortunately, assigning such a project requires an enormous amount of time on the instructor's part. Even simple projects require a substantial amount of infrastructure to handle and store data and recover the data at the proper time. And forcing students to do their own infrastructure makes the project extremely long. They end up spending a lot of time programming without learning anything about parsing, because what they're doing is building infrastructure. You can also, my preference is to provide students with the infrastructure, but that requires a great deal of programming time on my part. And so I've not found a simple solution to doing this project. It seems like it's either one sort of undesirable way of doing it compared to another sort of undesirable way of doing it. But once the students get their projects working, they have learned a substantial amount about parsing. Now, Turing machines, which is the last portion of the course, is something we spend actually fairly little time on compared to the other two sections. We start with Church's thesis and spend only a short time on Turing machines themselves. I might give a simple example, but because of Church's thesis, nobody does Turing machines. We have some subtopics that we consider important here, and the first one is undecidability. We do no proofs, but give the students a short algorithm that searches for a counterexample, Fermat's last theorem, and will run until it finds one. It's just a set of nested loops with some trivial code in the middle of it. And then we point out that if the halting problem were Turing solvable, we would be able to tell just from looking at this trivial code whether or not Fermat's last theorem were true. We're getting something for nothing. Everybody knows that that can't happen. So this motivates the students to understand that there must be such a thing as a Turing unsolvable problem. The final part of the course is devoted to a review of NP completeness, which we actually cover in our undergraduate algorithms course, but after discussing this with my colleagues, we decided that a review would be appropriate because it's something that students have a hard time grasping. So start off by treating CNF SAT as an accomplished fact and present two proofs, 3 SAT and vertex cover. We then show two approximations, bin packing and subset sum. And I show a number of other NP-complete problems, different sets in different semesters, just to familiarize students with what an NP-complete problem looks like, so will be better able to identify one if they encounter it in their life as a programmer. This course accomplishes two things. Students are exposed to theoretical concepts without the drudgery of long and dull proofs that don't appear to have any practical application. It provides useful tools that may be valuable for certain types of practical problems. The students' feedback from this course has been extremely positive. The students generally find that the material interesting and found it potentially useful. This course is now a required course in our curriculum. Thank you for your attention.